Welcome to this explainer. Okay, so today we're going to look at linear algebra, but we're going to do it completely differently than you might be used to. Honestly, we're treating it like a literal crime scene. We're going to learn how to investigate vector subspaces just like a detective would. Because, you see, a mathematical space, it isn't just some random collection of numbers thrown together. It's actually this incredibly strict universe, and it has absolute, unbreakable laws. So, when we stumble upon a smaller group of items hiding out inside that universe, we've got to interrogate them. We need to figure out, are they actually playing by the rules?
So how do we actually prove that a mathematical subset is playing by those rules? Well, figuring out if a subset is truly a subspace is all about, interrogating it, seeing if it really holds up under pressure. Because you absolutely cannot just look at a mathematical subset and trust it at face value. No way. You have to put it on the stand. You have to ask, does it break apart when you add things together? Does it totally fall apart when you scale it up? We really need a solid, repeatable method to uncover the truth here.
To wrap our heads around this, I want you to think of a vector space as this big, broad universe, and it's governed by 10 very strict laws of algebra. Now, our target, the subset, let's just call it W for now, it has to prove that it's a perfect, totally law-abiding miniature version of that bigger universe. It's living inside the larger vector space, which we'll call V, right? And to survive there, it has to use the exact same operations, the same addition, the same scalar multiplication. And here's the kicker. If it fails even one structural rule of that parent universe, well, it instantly gets stripped of the title subspace. No exceptions.
Okay, so to actually interrogate our suspect, we're going to use this foolproof three-step test. And listen, it has to pass every single step to be considered a true subspace. First up, does it contain the zero element? I mean, every valid space needs a point of origin, right? Without it, you've got nothing. Second, is it closed under addition? Basically, if you grab two elements from the subset and add them together, does the new result stay trapped inside the subset? And third, is it closed under scalar multiplication? Like if you multiply an element by literally any real number, does it stay inside the boundaries? If it passes all three, boom, it's a subspace. But if it fails even one, case closed, it's out.
Now, we need to talk about our strategy here, because this is a crucial point. To prove innocence, we have to use abstract variables to show that it always works. But to prove guilt, we literally only need a single piece of concrete evidence. Think about it. If you want to prove a subset is a subspace, you can't just pick the numbers 2 and 4 and say, hey, look, it works. That doesn't prove anything. You have to use abstract variables, like x1 and y1, to prove it holds up for literally every possible combination in the universe. But if you want to disprove it, if you want to show it's not a subspace, you get to play the hostile prosecutor. You only need to find one single specific numerical counterexample where the rule just breaks. That's it.
And this actually brings us to the absolute best shortcut in our entire detective toolkit. I love this trick. If the zero element isn't in the subset, you can just immediately close the case right then and there, because it is definitely not a subspace. I mean, why would you sit there and do hours of complex algebra, checking addition and multiplication, if the origin point isn't even there in the first place? For example, let's say a subset is defined by the equation x plus y equals 1. Just plug in 0. 0 plus 0 definitely does not equal 1. Boom. It doesn't contain the zero element. It is not a subspace. We just saved ourselves so much time.
All right, let's run through some rapid-fire evidence on coordinate vectors. You'll see that subsets like integers or a unit circle or even just positive coordinates, they actually all fail that third test. Just think about a subset made entirely of integers. Sure, it has 0. It passes step 1. But what happens if you multiply the integer 2 by, say, the scalar square root of 2? Suddenly, you get an irrational number. It literally breaks out of the subset. Or what about the unit circle, where x squared plus y squared is less than or equal to 1? Pick a totally valid point inside it, like 1, 0. Now multiply it by the scalar 5. Your new point is 5, 0, which is way outside that circle. Even a subset that demands a positive third coordinate is going to fail. Because if you take a positive coordinate and multiply it by a scalar of -2, well, it becomes negative. It broke the rule.
Remember the golden rule here. It only takes just one single counterexample. Like we just saw, if you multiply an integer by the square root of 2 or scale a positive coordinate with a negative number, the subset instantly breaks the rules. And that's the beauty of it. You absolutely do not need to prove that it fails for every single number out there. You just need to show that under the parent universe's strict rules of scalar multiplication, our suspect subset just couldn't keep its elements contained.
Okay, so let's shift gears and look at a subset that actually passes the test. Take the line x plus y equals 0. Let's see how this creates a completely watertight alibi using those abstract variables we talked about instead of just concrete numbers. So if we take two totally abstract points, let's call them u and v, and they both equal 0 when you add their x and y coordinates, well, adding u and v together algebraically groups to x1 plus x2 plus y1 plus y2. And since both of those initial pairs equal 0, the total is 0. It stays perfectly on the line. And you know what? The exact same thing happens with our scalar. Let's call it alpha. You multiply the point by alpha, you factor the alpha out, and you're just left with alpha times 0, which is just 0. The alibi is completely solid. But hold on, because our investigation is about to seriously escalate. You see, these laws, they apply to entirely different mathematical beasts. A vector doesn't just have to be a simple coordinate like x and y. A vector space can literally be made entirely out of polynomials. That's right, an equation with an x squared and an x cubed actually functions exactly the same way under the law as a standard geometric vector. It's kind of wild to think about.
So let's bring a new suspect into the interrogation room. A subset containing only polynomials of exactly degree 4. Think, x to the 4th power. Now, let me warn you, this is a very, very common trap in linear algebra. The subset claims, hey, I only allow equations where the highest power is exactly 4. And on the surface, it seems stable. But is it really? Let's put it under the microscope and subject it to the addition test.
And here is where the trap springs. If you take two completely innocent-looking degree 4 polynomials and add them together, those 4th powers, they might actually cancel each other out and leave you with just a degree 1 polynomial. Let's look at the evidence. If polynomial 1 is x to the 4th plus 1 and polynomial 2 is negative x to the 4th plus x, well, add those two together and the x to the 4ths literally annihilate each other. Poof, gone. You're just left with x plus 1. The degrees suddenly drop down to 1. It completely broke out of its exactly degree 4 subset rule. Guilt proven.
So this perfectly explains why bounding a polynomial's degree from the bottom, saying it has to be greater than something, totally fails the addition test. But bounding it from above, saying it has to be less than or equal to something, that beautifully passes. Think about it. If you say degree 5 or greater, you're going to fall right into that exact same cancellation trap we just looked at. You could easily add x to the 5th and negative x to the 5th, and suddenly drop way down to a degree of 2 or 3, completely breaking the rule. But if you flip it and say degree 3 or less, well, adding two small polynomials together can never magically spawn an x to the 4th or an x to the 5th out of nowhere. It stays perfectly closed, it's completely airtight.
And the crazy part is, we can escalate this investigation all the way up to matrices and super complex functions, and our investigative rules, they don't change at all. They remain exactly the same, because the laws of linear algebra are universal. It really doesn't matter if you're dealing with a grid of numbers in a matrix or this sweeping, continuous function moving across a graph. The three-step test, checking the 0 element, testing addition, and verifying scalar multiplication, is literally the only tool you need in your belt.
Take symmetric matrices, for example. A symmetric matrix is basically one where if you swap the rows and columns, the matrix stays completely unchanged. It's like a mirror image. And when you add two symmetric matrices together, their sum is perfectly symmetric too. Plus, multiplying by a scalar still keeps it symmetric. This means the super complex subset is officially a fully valid subspace. If matrix A is symmetric and matrix B is symmetric, the really beautiful properties of matrix algebra just guarantee that A plus B is going to be symmetric as well. And the exact same logic holds true for even continuous functions. No matter how complex the suspect gets, the math holds strong.
Which really leaves us with kind of a fascinating thought to chew on. As you dive deeper and deeper into linear algebra, how is your detective toolkit going to handle spaces that literally never end? I mean, we've looked at coordinates, polynomials, and matrices today, and they're all finite in their own little ways. But the true universe of linear algebra actually expands way out into infinite dimensional spaces. So the real question is, will the trusty three-step test still be enough to find the truth when those boundaries disappear entirely? Well, that is a mystery for another day. Thanks so much for joining me on this explainer, and hey, keep questioning the math around you.